heat island boundary anomalies, photovoltaic arrays in central Arizona using the Landsat Level 2 provisional surface temperature product. So really what I'm going to do is go through a background, go through the project itself, talk about the questions that I was asking of this data, and then talk about the methods and results and the conclusions. So really, the driver of this project was really looking at power generation, kind of where we get it from, and more specifically to look at solar panels. And so traditionally, we're looking at most of our power generation come from coal, natural gas, or some sort of nuclear power plant. And most more popular nowadays and becoming much more efficient are these solar panel array farms right here. And of course, with every type of power generation type, we do have some challenges. And really the biggest challenges with this power generation is the release of heat, just because of those dark solar arrays. And so they're absorbing solar energy and releasing that back as heat. And so really what this study aims to look at are those heat effects, and especially around those solar panel arrays. And so there's been a lot of studies around heat islanding effects, especially as it pertains to larger cities and use of concrete, asphalt, and such. And so right now, using those same dark materials, kind of looking at how far out does this heat islanding effect go, or how much can we expect to see it with these solar panel farms. And so understanding that is difficult, just because we're really limited by the range that we can do these measurements. And so typically we can measure underneath them, we can measure outside of them at these points, but getting the spatial information is quite difficult. So right here we're going to use Landsat 8, so using remote sensing tools. And then more specifically, developed by Cook et al. In 2014 is a Landsat Provisional surface temperature product. And really what this product does within their algorithm, it uses the Landsat 8 collection 1 thermal bands. It uses top of atmosphere reflectance from Landsat 8. And then it taps into other ancillary data sets such as ASTER, the Advanced Spaceborne Thermal Emission Reflection Radiometer, to look at the global emissivity data set. Then to look at the NDVI from ASTER. And then it uses atmospheric profiles of geopotential height, specific humidity, and air temperature extracted from reanalysis data. And so that's from the Landsat 8 data. And then this is all resampled down to 30-meter spatial resolution. So something to think about as we're looking at this data. And so my big questions were, are these PV array sites anonymously hotter or cooler than their surrounding environments within this ecosystem? And if so, how far does that extend? And then my second question was, how does the size of these sites influence that boundary land surface temperature? And so the answer to this question, I looked at 4 different sites in central Arizona, west of Phoenix, right here, of 4 different sizes. And then I used really a single scene to look at that. And really that was a control for those different processing that happens with that land surface temperature product. And I looked over 5 years, and so I started at 2014 because that was when the last solar array farm was completed. And then my derived data set, I actually averaged these out over 5 years to kind of create another raster data set that I used to test my other question. But to start off, what I did was I chose to kind of create a base or more of a control of kind of what I'm seeing around on the landscape. I chose 50 random points across natural desert ecosystems, being sure to exclude urban areas and mainly the agriculture areas and clouds, and created kind of this base right here. And so of course, it was really interesting. So I tried to choose July as our base month because that's the hottest month of the year. And I felt like that'd be a good time to get some solar heating in. But I found that in 2014, 2015 were a little bit more cloudy and a little bit cooler. But really looking at the average standard deviation for all of them at 1.41 degrees Celsius, plus or minus 0.12, and thinking about how climate is averaged over time, I decided to kind of keep those 2 dates in there and kind of give a more long-term average, and I guess we can reassess that after we get measurements this year. But so that's kind of the data that's behind it. And really kind of the main bulk of this was really this idea of using buffer zones and looking outside this PV array sites. And so really there's a polygon for each one of these 4 sites. And then as we move out from these sites, right here we have our buffer zones. So we go from 30 to 180 all the way across. And keeping in mind that as we're sampling these data sets, we're only sampling within these buffer zones. And really at first look, what we're looking at right here are our temperatures across our buffer zones. And this is kind of our first look at the qualitatively at our data as we move across. And really, again, keeping in mind that we can't resolve beyond a 30-meter resolution, which is why I use this buffer zone distance. What I found was we have this really large, just at first look, this really large jump at the 30 meters. And as we move across, we're getting really flat and the variability increases over the buffer distance. And so really what I kind of was testing when I looked at this was really kind of looking at that 30 meters. That's really interesting to me. And I test this with a couple different ways. And so the first way was using this linear regression because I was kind of interested to see if my first question of the size of, well, one of my questions of the size of PV installations and if that has an effect on the temperature around it. And so as we expected, the temperature of larger sites is much higher, which is kind of what I expected. But as we move across, everything starts to decorrelate a lot, especially starting, well, I mean, at our first buffer zone at 30 meters. And so what we see right here is really everything just kind of falling apart as we go above. But really interesting to me, and I'll kind of state in my conclusions, was this idea that we're kind of getting more of a negative slope at the very top, going from this smaller site to this larger site and seeing this larger variation within the smaller sites than we do with the very largest site. And of course, keeping in mind that this is just 4 sites. So the kind of test for significance, I averaged all those, like I said at the beginning, sampled them, and aggregated these shapes together to then create our site, our distance 0, and then our different buffers. And really what I saw testing at a point p equals 0.05, I saw a significant difference between really every one of them. And what I really would like to do is kind of tease out this 30 meter right here, because we do see this as a transition zone, and I feel like that would probably be the best use of future attention would be on that 30 meter buffer zone. And so really back to my questions, are the sites anonymously hotter or cooler than their surrounding environments? Well, there's really an unclear relationship between the size of the site and the distance at which the temperature differences are seen. The smallest sites show the highest temperature differences, and that's probably due to those larger buffer zones mask out that variability that might happen within that buffer zone. So different land cover types or different land or cover percentages and stuff like that. So that would be something to kind of tease out a little bit later. And then really the second question was, does a size influence the boundary land surface temperature? And so really there's no anomalous heating or cooling of the environment outside the PV array sites up to 180 meters. I was using a two-tailed t-test to look at if it was higher or lower, and really there was nothing above or below. And really all the temperature differences were held within 2 standard deviations of the control points, kind of telling me that really there's not a huge variation of temperature. And that was, again, shown through the t-test. So really my closing thoughts, looking at everything, and understand that environmental impacts are not so straightforward, and that's shown through trying to look at these spatial relationships as opposed to just point measurements that we normally get. And we can use these remote sensing tools to kind of look at that and kind of tease out those relationships. And really kind of my biggest thing is re-looking at the models to look at how the equations are built, especially when we look at dark surfaces, because most of them are built for NDVI models, which doesn't apply to dark solar panel farms. And that's it. Thanks.